My name is Anjana Vakil. I am here today to live code the Lambda calculus with you all, which is definitely something we should never do on our own at home, but it's way better when we do it together. So this is going to be a participatory talk. I hope you are ready to participate, despite the fact that it is that really, really sleepy moment of the afternoon, 4 p.m. I know. So I am going to try and keep us all awake here as we go through the Lambda calculus, which I'm going to explain what that even is in a minute. As I said, my name is Anjana Vakil. You can find me on Twitter at my name. I work for a company called Mapbox in San Francisco. Anybody know or use Mapbox? A few hands? Nice. All right, awesome. So if you haven't heard of us, we build a developer platform for creating really beautiful, performant, interactive, and highly customized location experiences. So maps, yes, but all kinds of other types of data that have to do with location. You can check it out and sign up for free, mapbox.com. And before we get started here, I would love to tell you about a few communities that I am super lucky to be a part of. One is the Mozilla Tech Speakers. Tech Speakers in the house, woo! Yeah, we are a traveling gang of ruffians who lose their signal occasionally and travel the world talking at conferences like this about the open web. And every year or two, we accept new folks into the group. So if you're curious, check it out, Mozilla Tech Speakers on the events.mozilla.org website. Another community that I am really lucky to be a part of is called the Recurse Center. It is a programming retreat, like a writer's retreat, but for coders. In New York City, it's a space and a community where you can go and completely self-directed create your own space and time to get better at coding, whatever that means to you. It's super cool. Check it out, recurse.com. Did I mention it's free and unstructured? And in New York, it's super cool. Check it out, recurse.com. The last community that I really want to let folks know about, if they haven't heard of it before, is called Outreachy. Outreachy with a Y. This is an initiative to get more women and underrepresented minorities involved in open source by offering paid remote internships on all kinds of different projects. And this happens twice a year. They offer internships twice a year at all kinds of different organizations, including Mozilla. So if you or someone you know might be looking for a way to break into the open source world and is a woman or a member of an underrepresented group in tech, send them to outreachy.org. And if you or your company maintain a large open source project and would be interested in getting interns who come and work for you full-time remotely for 3 months, also check out outreachy.org. It has all the information for both mentors and mentees. Okay, all right, so those are my obligatory community awareness messages. Now it's time for us to dig in to some live coding the Lambda calculus. Just so you know, the notebook that I'm going to be presenting to you here today is available on my GitHub gist page. I personally think the only way to really wrap your head around this stuff is to work with it yourself, to really get hands-on. So please feel free to follow along if you've got your laptop, or check it out at home after the conference. All right, so I've said the Lambda calculus like 8 million times. The what a calculus? What is a Lambda calculus? It's a Lambda calculus like the Greek letter lambda, this triangular pointy thing with a tail that you probably recognize from being the logo of every functional programming language ever. Haskell, Clojure, etc. And we even saw it earlier in the state, the X state system. Huh? It was embedded in the X secret. Okay. In any case, it's a mathematical and logical formalism that this really awesome guy, Alonzo Church, started developing in the 1930s as a way of investigating the mathematical and logical foundations of really elementary things like numbers. And so really trying to get at the core of math and logic and like really big philosophical stuff like that, which I totally love. And he basically fell down a huge rabbit hole with it that the computer science community has still been falling down this rabbit hole for the last, almost going on 100 years now. And this formalism became really the foundations for the paradigm of functional programming. What's really cool about the Lambda calculus is that it gives us, with one single construct, a Lambda function, which is a pure single argument function. We're going to look at what that feels like in a minute. With this one construct, one tiny little Lambda function, you can create everything in computation, the entire universe of the computable world, which I don't know about you, but I think that's pretty freaking rad that you can have one little function explode like the Big Bang and create the entire universe. So that's what we're going to be looking at today. So the question we're going to be asking ourselves is, if we treat a JavaScript arrow function, like a tiny anonymous function, as if it were a Lambda function, what can we make with it? And I've already spoiled this for you, everything. We can make everything. We don't have time to do that in, 40 minutes today, but we're going to make as much as we can. And just so you're aware, this is going to be the least useful talk you see today, by a wide margin. What we are here to do is hurt our brains and mess with our ideas of what computing even is, and look at some really, I think, and I hope you also think, some really cool and elegant constructions for representing computation. But what we are not here to do is learn some kind of practical programming tips that you can go to work on Monday and start writing all of your code in the Lambda calculus. Do not do that. And if you do that, and your boss gets mad at you, it is not my fault. In any case, this is intended to be silly, learning-oriented, and hopefully expand our minds a little bit. So if we're doing that, then we're doing things right. Okay. What is a Lambda function? So I mentioned already that a Lambda function is a tiny, pure function. Pure in the sense that all it does is it looks at its inputs, and in Lambda calculus, it only has a single input. A single value gets passed in. And looking only at that, it returns some output. And it always returns the same output given the same input. So it's deterministic, it's small, it's anonymous. We don't give them names, although we're going to be assigning names to some of ours just to keep our sanity today. And we create one in the Lambda calculus. We would define a function, or in Lambda speak, we would do function abstraction by using the Lambda symbol, then the symbol for whatever input variable we want to use. It's often X or Y or other cryptic things like that. And that indicates what the input is. Then we have a dot. And everything to the right of the dot is basically the body of the function. So in this case here, I have basically an identity function. And if we were to translate that into JavaScript arrow functions, it would basically look like a really, really simplistic arrow function. We've got one argument on the left. I'm not even going to put parentheses around it because we don't need them since we only have a single argument. And it's going to return some thing on the right. So we're going to treat this arrow like the dot, and the Lambda is just kind of implied by the arrow. Now, as I mentioned, Lambda functions can only take one argument. So if we conceptually want to do something with multiple pieces of data, we have to kind of fake multiple arguments. We can't put them in a single function like we could in JavaScript. We could use parentheses and put a comma between arguments and have as many arguments as we want to an arrow function. But in the Lambda calculus, we only ever get one. So what we have to do is, if we want to take in multiple pieces of information, we define a function, lambda x, and that's going to return another lambda expression, so another function. And in that one, we can call the input variable y. So now basically, this x function is going to take in the first thing that I want to operate on. That's going to return a function, which will then be able to take in the second thing. And then the body of the second function lets us combine those inputs in whatever way we want to, for example, adding them together. So even though JavaScript lets us define arrow functions with multiple arguments using this parentheses and comma notation, we're going to constrain ourselves. We're going to play the game that we only have the equivalent of a lambda function. So instead, we're going to write a multi-argument function like this with lots of arrows chained together. We're going to have an arrow function that takes in x and returns another arrow function that takes in y. And that function returns some operation on both x and y. Cool? With me so far? Seem reasonable? These are the rules. Okay, cool. So then the question is, once we've got a function, once we've defined one, or once we've done function abstraction, how do we use one? Or in Lambda speak, how do we apply that function? In the Lambda calculus, often what you'll see is syntax with parentheses around if you have a very complex Lambda expression, Lambda series of functions, and they often get very complex very quickly, as we'll see. And then you will have a space. The argument that will be passed in, which will, in this case, the 5 becomes our x value here. And then that whole thing will return another function, which then you can apply to 1. Then 1 gets passed in as the y. And essentially, we're doing then the operation on 5 plus 1, and we get 6. So these spaces and this kind of notation shows up a lot in functional programming languages as well. This kind of inherits from the syntax there. Now, in JavaScript, we're going to need parentheses around the arguments that we want to call a function with, the inputs that we want here. And I can use parentheses around my complex, multi-argument lambdas here to indicate that we're applying this whole function to the input 5. That's going to return another function that then I can call on 1 and do the same thing. Okay, so this is just some syntax rules. We down with it? Great. Okay, I see that everybody is super awake. Excellent. Okay. So, all right, let's dive in here. I said that with a single arrow, we can create the entire universe of programming. So what do we need to do programs? Like, how do we compute? Well, we need a lot of things, but let's start with basics. One really useful thing for computers is numbers. Because especially like whole numbers are fun. Counting is great. Who doesn't love counting? Exactly. Everybody is super fond of counting. That person does not count. And now we have to ask ourselves, okay, we have no primitive data types here. All we have is a function. What can we count if all we have are functions? I'm going to let you think about that for a second while I take a sip of water. So what we can do is we can create functions and we can apply functions or call them. What if we count those applications? What if we count the number of times that we call a function and consider that, like, if I call a function once, I'm kind of counting 1. And if I call it again, I'm counting 2. And if I call it again, I'm counting 3. So this is going to be our way of representing integers here. Okay, so what this is going to look like is if I want some kind of integer, we'll start at 0. That seems like a good place to start. Everything in the Lambda calculus is a function, right? Now, a numbery function is going to be a bit weird. Bear with me. It's going to be something that, okay, we're going to start out with a function that takes in some other function f. We don't know what it is, any function. And that's going to return a function that takes in some input x. And so this is kind of like a multi-argument function that takes a function and then some input. And it's going to apply the function some number of times, but we don't really know what that's going to look like yet. The point is all of our numbers are going to have this kind of signature. They're going to be this shape of function. So now I said that the number of times that I call the function is going to represent the number. So if I want to represent 1, I've got a function and I've got some input. To represent 1, I'm going to call the function once on that input. And then to represent 2, I'm going to call the function on the input, and then I'm going to call it again on whatever the result of calling it the first time was. Okay? And can anybody guess how I'm going to represent 3? So this is going to be f of f of f of x. So 3 applications of x. Cool? Oops. What'd I do? I didn't have a parentheses. Great. Okay. Now 0, then, if I'm going to count the applications of f as like how I count things, if I want to count 0, I'm going to return just x, I think I heard somebody say. Right? Remember how I said we have to do this together? Don't make me live code the Lambda calculus on my own, people. All right. So I'm going to represent 0 as no applications of the function. And going up from that, we're going to apply it more and more. Okay, so now I have told you that these weird functions are numbers somehow. You probably don't believe me. I wouldn't believe me if I were you. So let's try to convince ourselves. We're going to cheat because in the Lambda calculus, we don't have recourse to like built-in JavaScript data types like numbers, right? But just for sanity's sake, we're going to make a cheating little function called toNumber that is going to take some number n. And it's going to apply that to an f and an x, which is what we do with numbers. We apply them to an f and an x, where the f is going to be a little function that just takes in some integer and adds 1 to it. And we're going to start it out with x being 0, so that if I don't call f at all, I should get 0. And if I call f once, I should get 1. And twice, I should get 2, et cetera, et cetera. You with me? Like a converter. OK, great. So if I've done this right, then I should be able to call my toNumber converter on one of the number functions that I just made and get 3. OK, great, but maybe I rigged this. You don't know. So let's see if it works live. OK, wonderful. What if edge case? OK, great. So are you convinced? We have something numbery here. Cool. You sound super convinced. I've never seen a more convinced looking group of people in my life. So what we have just done, we have represented numbers in the Lambda calculus, and this is called, this type of encoding numbers like this, these are called church numerals. So representing integers like this, we are creating church numerals. So for those of you who would like to Google something on your phones right now, you can Google that. If you want to learn more. It's a wild, wild world. It gets way more intense than that. But OK, so we have some numbers. We can count all day long. But maybe we can spice things up and do a little bit more with these numbers. How about some arithmetic? Yay! we didn't do it yet. We can't give ourselves credit yet. But we are really excited about being in like first grade right now, right? OK, so now we've got these numbery things. Let's say we have 2 of them. We'll call one n and one m. And these are basically things that count calls to a function, right? How could we add those things together if what they do is apply functions a certain number of times? A question for you to ponder, again, while I hydrate. So if I've got, let's say, n is 2 and m is 3, what I'd want to do is I'd want to call f 1, 2 times, and then I'd want to call f 3, 4, 5 times, so 3 more times, and I should have a total of the sum of the 2 numbers. So that's what we're going to do. We're going to call the function n times and then call it m times. All right, what is this going to look like? Well, what kinds of things is it going to take in? What is it going to need? First, we're going to need some number n, and then we're also going to need m, thank you. And then what kind of thing are we going to return? If we could have an addition function that takes 2 numbers, it's going to return a thing that is a octopus? No. It's going to return another number. Exactly. And numbers have this weird shape, right, where they are things that take an f, functions that take an f. I say things and functions interchangeably because the only things we have are functions. That's our whole world. And that's gonna return a function that takes an x. And so like we're gonna have to get used to seeing this type of shape and recognizing it as like numbery situation, a numeral. Okay, now, I said I want to sum these numbers together. I want to call f n times, which I do by applying n to f and then applying that to x, right? This would call our function f n times. But then I also want to call it m times, so I'm going to take whatever the output of this whole thing was and call m, apply m to the same f, and then apply that whole thing to this as the input of the new thing. Yeah? Did I do this right? Let's find out. Okay, so if I did this right, which who knows, it's live, I don't know, I'm super jet lagged. If I did this right, we should be able to add 1 and 3. And again, we have to get used to looking at this type of syntax when we don't have multiple arguments, right? We should be able to add 1 and 3 and then get out a thing that if I convert it to a number, it should be 4. Yay. Okay, but again, I could have rigged this. So what about if we add 2 and 2 and 2? Sure, let's try that. Also 4. Let's try incrementing this a little bit. 3. It works. Yay. Are we convinced we have some kind of basic addition here? Yes. Nice. Excellent. All right. How about some more arithmetic? How about multiplication? Ooh. Think on this one. So how do we multiply n and m? Again, let's say n is 2 and m is 3. Ponder it. Ponder. So what we want to do, if we're trying to multiply 2 and 3, let's say, we want to count 1, 2, and we want to count that as kind of like, okay, that was one time that I counted 2, right? Then I want to count 3, 4, that's 2 times that I counted 2, and then I want to count 5, 6, and that's 3 times that I counted to 2, yeah? Okay, so in terms of function applications, we want to call the function n times m times over, yeah? So how are we going to write that down? I don't know. All right, well, we already know the signature of this function, right? It's going to be something that operates on 2 numbers. So, takes an n and takes an m, and it's going to return a number, which is going to be this weird f, x situation. Okay, so I said, first of all, I have to call f n times, which we saw always looks like this, right? Now, what I want to do is like this application, what this does is this gives me a function that when I apply it to the next thing, it's going to call f n times, right? But that's a function, which means that if I wanted to call that function a certain number of times, I could pass it in as the f to another number. So if m here is 3, it's going to take whatever this function is, which is going to be counting to 2, and apply it 3 times. So if we did this right, which again, big if, I should be able to multiply 2 and 3 and get 6. Oh my God, it worked. What if I try multiplying 2 by, we have 4, right? Oh, okay, I could be cheating though. Let's try changing this. Oh my gosh, we're doing multiplication, y'all. We know how to add and multiply. We just aged like 7 years. No, I don't, maybe in the US, but anyway, we aged a lot in a few minutes here, so that's exciting. Okay, so we're not gonna talk about subtraction or division because those are way harder, but suffice it to say, we've already got some cool computation here. We've got like a really simple calculator, right? That took humans a long time to figure out, and we just figured it out in like 20 minutes. Cool. So that means we can already do some pretty sophisticated computation. For example, we can think deep thoughts like, what is the answer to the life, the universe, and everything? Well, it's so simple. If I just add 4 to 1 and then multiply that by 2 and then multiply that by 4 and then add 2 to that, then I should get 42, the answer to life, the universe, and everything. Yay! All right, that was a Hitchhiker's Guide to the Galaxy joke. See, now we've done the work of the entire planet Earth. Pretty cool, huh? All right, so now addition and multiplication, they're pretty cool, but like a calculator is not all of computation, right? So what else do we need to do programming? What are some things? Help me out. Silence, crickets. We need crickets to do programming. No. All right, well, so one thing that programmers really like to do is to work with truth values and control flow. Exactly. So what we can do, the next thing we need to write programs, is figure out how to write Booleans and conditionals. If we have truth values and we have some kind of conditional expressions that allow us control flow, then we're really cooking with gas, right? Then we can do some computing. So what are we gonna, how could we possibly do this? Again, we have no primitive Boolean values here. We have no if statement. We're gonna have to write it ourselves. So if we think about it, these Boolean values and conditional control flow, so if-else statements, they kind of go hand in hand, right? I am going to have some kind of condition that's a Boolean. And here I'm just using this, this ternary syntax here for conciseness. And if that Boolean is true, then I'm going to do some like then clause. I'm going to execute that. We'll call that our then clause. And if the Boolean condition is not true, if it's false, I'm going to have some kind of else clause that I do instead, right? Programming. Yay. Okay, so how are we going to set up these things so that this is possible? Well, we're going to define them all kind of together so that they play nicely with each other. So, all right, let's think about this. I want to have some kind of if-then-else construction, which is going to be something that takes these three things. It's going to take some kind of Boolean value, just bool for short, and then it's going to have some kind of then thing that I'm going to do if the Boolean is true. And it's also going to need some kind of else clause. Oh, but oops, else is a reserved word in JavaScript, so let's rename it else and then, because who needs so many vowels? Not us. And it's going to do something. I don't know. All right, but now let's take a step back. So the condition's true and false, which I'm also going to rename here true and false, so as not to conflict with JavaScript's true and false. These are going to be things that what they help us do is like choose a path here in our if, then, else, right? So true is going to be something that when the Boolean condition is true, I want to hit the then. And when the Boolean is false, I want that to be the thing that makes me hit the else. So what I'm going to do is set these up as kind of choosers. A Boolean is going to be something that takes a then and an else and basically picks one. So they're both going to have this kind of signature that they take in a then and an else. And the false is going to be the one that picks the else. And the true is going to be the one that picks the then. And this feels a little bit like cheating because it feels like kind of a circular definition, but we're just trying to make a system that we can work in here. So if I have true and false set up this way, then for my if then else, where I've got a Boolean, a Boolean, a then, and an else, what I can do is, since Booleans are functions that when applied to a then and an else will pick one of them, I can apply my Boolean function to the then and to the else. So if this Boolean now is true, it's going to take in this then and return a function that's going to take in this else and give me back the then so that I can do that. And if it's false, it's going to do the other. Yeah? It's exactly what you all were thinking, right? I know. Okay, now, again, you have no reason to believe me that this works, right? Because here I am, I'm just some jet-lagged JavaScript developer up here on the stage telling you, yeah, we can totally program in this. Why would you believe me? Well, let's try it out. Let's try to write a program. So this is a little very exciting program that is going to predict the number of coffees that I have had today based on the tiredness Boolean, which let's say for the sake of argument that I were not tired, that tired were false. And the number of coffees that I drink in a given day is like, if I am not tired, I'm probably only going to have one coffee. Just my daily regular coffee, because I have to drink coffee. Obviously, I can't be 0. And if I'm really tired, then I'm going to have like 3 coffees, because I'm really going to need to jolt up the caffeine. So if I've done this right, then if tired is false, and I have a little program that uses the value of tired to choose a number of coffees, and let's say for the sake of argument that I am not tired, then I should get the number of coffees today is... Okay, all right, interesting. But this was a really like a thought experiment, because clearly that is definitely the correct value of tired. I am super jet lagged and super tired. So really the number of coffees that I have actually factually had today is 3. Y'all, we just wrote a program. Right? So now I have control flow. Now I can add and multiply numbers in all kinds of different configurations. Okay, all right, sweet. Now we've got some Booleans. The next thing we might want to do is try to operate on them. How about we do some logic? Huh? Everybody loves logic. We're programmers. It's our jam. So let's think about this. How can we do some logical operators? So just to help us think through this, I've made another little cheating converter here that's going to take a Lambda Boolean and apply it to JavaScript built in true and false, so that if the Boolean is true, then it should pick the JavaScript true, and if the Boolean is false, then it should pick false. Yeah? So let's just test this out. Does this converter work? Okay, true is true, and false is false. Cool? Okay, again, we're cheating, because we can't really do this. We don't have true and false like JavaScript does, but this is just to keep us sane. Okay, so now, what if I were to make a not operator, negation, right? If I want to flip the value of a Boolean, how could I do that? Another thing for you to ponder. All right, well, let's think through it together. So first of all, what kind of thing is not going to take in? Well, it's going to operate on some Boolean, right? And it's going to return another Boolean, which we said is something of the shape that it takes a then and it takes an else. Yeah? Okay, so now, normally what I do is I apply my Boolean to the then and the else, and it picks the right one, right? The first one if it's true, and the second one if it's false. What if we were to get real tricky on the program here and just just swap it around? Tricksy. If we do that, then we might be able to fool the computer into choosing the opposite value. So let's try it out. If that worked, then I should be able to call not on false and get true. And likewise, ha! Hacking. Okay, so we've got some logic. We've got a logical operator, but how about we keep going with this? More logic. How about we do an OR operator? Like an inclusive OR operator, right? So let's say that, so this OR is going to operate on two Booleans, A and B. And it's going to, we want it to return false when they're both false, and true otherwise, yeah? So let's think through, how can we do this? We don't know what A and B are, but we know that they can only be true and false, right? They're Booleans. So let's say we start with our A, and Booleans are things that we apply to two things. Now let's assume for the sake of argument, that A is going to be true here. Do I care what B is? No, right? I don't care. I want to return true. If I know that A is true, I want to already return true. So if A is something that, if it's true, it's going to pick the first thing, then why don't I put something that I know is going to be true in the place of the first thing, like A? And let's imagine now that A is false. Well, then it's going to pick the second thing. Now, if A is false, then we do need to care about the value of B. And we want to return, as the final output of this whole operation, whatever the value of B is, right? If A is false and B is also false, then fine, we get false. If A is false and B is true, then great, we get true. So we could just, if A is false and it's going to select whatever goes here, we can use the value of B, because that's going to be the end result of this whole operation. So let's try it out. If this worked, then I should be able to call OR on true and true, and I get true. Okay, but now what happens if one of them is false? Okay, it's still true. All right, what if both of them are false? Okay. And just to complete our truth table here, aha! So we did a truth table. We did all 4 combinations. Amazing, and it worked. You all do not seem as excited as I am about this. But we can now like do some pretty cool coffee calculations with like multiple variables. We can combine their truth values. Okay, but we don't need just OR. We also need AND, right? Now, this is going to be the same type of thing that takes in an A Boolean and a B Boolean. How are we going to write this operator? So the overall principle, as some folks are, I see the light bulbs, right? The overall principle is going to stay the same. Booleans are things that choose two things. Now, if A is false, let's imagine. If A is false, do I care about B? No, doesn't matter what B is, and only returns true if both of them are true. So if A is false, I already know that I want to return false. And if A is false, it's going to pick the second thing, and I already assumed that A was false, so I could have it return A. And likewise, if A was true, then I'd want to go on and figure out what B is and return whatever B is, right? If A is true, B is true, then great, I want true. And if B is false, then I want false. So that means if A is true, it's going to pick the first thing. I can put B there, and it should return the right value for the whole operation. Let's find out. All right, so and true should be true. Oh, and it is. Amazing. And true and false should be false. Cool. So in the sake of time, I'm not going to go through the rest. Well, all right, it's super quick. We can just do it here. Fine. Okay, look, 2 truth tables. Yes. Excellent. Thanks, y'all. Okay, so now, getting down to the wire here. So we're going to see if we can power through the next thing we might need to do some programming. And since we're programmers, we really love data structures, right? We don't just want data, we want some structured thing to put it in that we can then diagram on our slides and talk about with our friends and argue with people about on Hacker News and etc., right? So we need some data structures. Where could we start with this? Well, what's everybody's favorite data structure? It's a list. Yeah, no, maybe not everybody's, but definitely functional programmers freaking love lists. They let us do so much. Basically, once we've got a list, we can do pretty much anything. So let's try to make some lists. Okay, what kinds of things can a list contain? Well, it could contain nothing, and we're going to use a special term for that, nil, whatever. It could contain one thing, or it could contain more than one thing. Have I forgotten any possibilities? I don't think so. Okay, cool. So let's see if we can do these. If we can do these, then I'm going to feel pretty good about the lists we've got. All right, to make these lists, we're going to start with a kind of a substructure where we're going to take pairs of things. We're going to take values and just pair them up like little buddies, because otherwise they might get lonely, and we don't want that. So we're going to take those pairs, and then we're going to use them to build lists. Let's find out how in 3 minutes. All right, I've got a little function here, make pair, that's going to take something that's going to go on the left of the pair and something that's going to go on the right of the pair and give me out a pair. Now, what is a pair? Well, in the weird Lambda calculus world, like you know how a number is a function that takes in some function and calls it a certain number of times? Well, a pair is going to take in some function f, and it's going to apply it to the left thing and the right thing. And that's just going to be our definition of what a pair is. And that's going to be useful, as we see later. So if I want to create a pair and then retrieve the values of it, I'm going to need some kind of functions like get left and get right to get those values out. So how can I do that? All right, if I have a get left or get right function, it's going to be something that operates on a pair. And it's going to want to choose either the left thing or the right thing. Sound familiar at all? Do we have any functions that are good at choosing from a thing and another thing? We have Booleans. Yes, exactly what you all were thinking, right? So what I can do is I can take this pair, and if I apply the pair to my Boolean, then what this is going to do is it's going to pass in the Boolean to the left and the right and apply it to both, right? So if I pass in true is F here, true on the left and the right is going to choose the left. And likewise, false, if I apply it to the left and right, is going to be passed in as F here and choose the right. Sound reasonable? Hopefully. All right, we'll see. All right, we're gonna pretend this works and use it later. So if I were to make a pair of two things, I would call it like this. I should be able to make a pair of two numbers, and then I should be able to call get right on that and get out the right number. Did I evaluate this? I don't know if I did. Okay. Let's see if this works. If this does work, I would expect to get, help me out, 3. The right of a pair of 2 and 3 should be 3, yeah? So let's find out. Okay. Whew. Okay, but again, I could have been lying to you and like rigging this. So let's see if what happens if I use the left. It gets 2. Excellent. Okay, now how do I turn pairs into lists? Well, we're basically just by convention going to say that a list is a pair that has a value on the left that's a Boolean that tells me whether or not the list is empty, and a value on the right that has whatever the contents of the list are, which I care about if the list is not empty. Okay? So if I want to find out if a list is empty or not, I want to get the value of this empty, and I can use my getLeft to do that. So I'm just going to alias that to isEmpty to find out if a list is empty. And the only list that is going to be empty is what we call nil, the empty list. There's only one list that's empty. It's nil. And so if the list is empty, we don't really care about its contents because there are none. So what we're going to do is we're going to represent the empty list as a pair of true, meaning it is empty, and whatever we want. Why don't we just put another true here? Because we don't really care. So nil is going to be a pair of true and true. And if I call isEmpty on nil, I should get true. Cool? Okay. Now, that's not a very interesting list. Can we make more interesting ones? Let's find out. So if I want to add something to a list, and let's say I would add something to the empty list to get like a single item list, what I'd want to do is create a new pair where there's going to be a new item and whatever was in the old list paired up together. And that's going to be the contents of a new list, which again is a pair, which now, since there's something in this list, I'm going to set empty to false. Yeah? So if I want to prepend something to a list, I have to take an item and an existing list and turn it into that thing, empty is false, and then a new item, a new old list. And I'm going to do that with my pairs. So I'm going to make a pair of the item and the list, and I'm going to take that whole thing and make a pair of false and that. Okay? So what I'm doing now, this is the way that I can prepend something to an existing list. All right. Oop, it didn't work. What'd I do? Parentheses? Yeah, okay. So now, if I want a non-empty list, what it's going to look like is basically this kind of nesting structure where I'm going to keep prepending things. So I'm going to get these nested lists. If you've done any like Lispy functional programming, you might be familiar with this type of listy nestedness. And so if I want to create, we said we can either have nil, we've already got that, or a single item list, or a list with multiple things in it, right? So I should be able to get these now. Uh-oh, I'm missing semicolons. Oh, no. I should be able to prepend something to the empty list, nil, and get a list that looks something like this. It's not empty, and it's got 1 in it. And I should be able to keep prepending stuff to get these nested lists of this shape, right? So I'm going to take my list of 1, prepend 2 to that, prepend 3 to that, and now I have a list with 1, 2, and 3 in it. Cool? All right, so now what I can do is I can get things out of my list using these head and tail operations. What they do, and again, from functional Lispy land, they will give me either the first thing in the list or everything else that is not the first thing, the rest of the list. And I'm going to use my my get left and get right to do this. So I'm already out of time, so I'm just going to run through this real quick. If I want to get the head of the list, which sits here, I'm going to have to take the whole list, get the right of it, and then take that and get the left of it. Yeah? So I'm going to do get right of the list and get left of that. Seems right. We'll find out. And for the tail, I'm going to get the right of the list. And if this worked, then if I want to get the 2 out of that list, I should be able to take the multi-item list. Ooh. Come on. And get the tail of it And then if I get the head of that tail, oh no, parentheses, y. I should be able to get my 2 out here, right? So it's in the tail of the list, and then it's the head of that. Let's find out. Nope, what'd I do? Without what?
Just head and tail.
Oh, oops, I didn't put get, yeah. Thank you. Okay, thanks. If I name my functions correctly, then I should be able to get out my 2. Yay. Woo! Okay, thanks for bearing with me. What we've seen then is that we have got so much stuff. We've got data, we've got numbers, we've got Boolean data, we've got data structures, lists to hold them. We can do operations, we can do arithmetic, we can do logic and control flow. We've been able to represent all of this using just Lambda functions. So what this is called, representing data and operations this way, is called church encoding, of which those church numerals are kind of like a special type of church encoding. So if you want to fall down a huge Wikipedia rabbit hole, go look up the church encoding page. It's awesome. You can do everything. Like from here, this is just the tip of the iceberg. We can go on and do all kinds of other math. We can have predicate expressions. We can have inequalities. We can manipulate lists with like mapping and filtering and reducing. You know, basically the entire universe of computation. So I don't know about you, but I think this is pretty cool. I'm way over time, so I'm gonna zoom through this. We're not gonna talk about how super cool it is that actually these types of things show up also in object-oriented languages like Smalltalk, has church encoding for Booleans and stuff. It's pretty wild. You can even do OOP in the Lambda calculus. What? In any case, there's a lot of references that you can check out to learn more. You can find all of this stuff on my GitHub gist page, and I want to give a huge thank you to the Uphill Conf organizers for having me and for putting up with my long speech here. All right, thank you all so much for playing along, and please, please go have fun encoding everything in the church Lambda E style. Thanks a lot.